Now we're going to talk about continuous variables and distributions. Up until now, we've been considering discrete variables and distributions. On the left, we have a discrete probability distribution. Discrete probability distributions, x values can only take on discrete values. So here we have x taking on 1, 2, 3, 4, 5. It doesn't have to be integer values, by the way. We could have 1.1, 1.2, and so on. But the idea is that these are discrete. We can't have anything between those discrete values of x. And so the probability distribution function f of x, we have these bars that essentially sum to 1 over the entire domain of x. Now we're going to talk about continuous probability distributions. We still refer to this as f of x. It's a probability density function is how we refer to it as. And instead of being bars like this, discrete, x can take on a bunch of different real number values. So for example, we could start at a very small number, here a negative number, and we can go up and we might get some distribution like this. X can be continuous in a range, or it can go from negative infinity to infinity. And there's different examples of probability density functions that take on different values of x as their domain. So a continuous random variable is a random variable with an interval on the real line, either with finite limits or infinite. Since continuous random variables are represented by real numbers, there's an infinite number of values possible, not finite as with discrete variables. So as a reminder, for discrete random variables, we are able to define a probability function. The probability that x, our random variable, takes on any certain value of xi is given by f of xi. And we saw that the sum of all of those xi's has to equal 1. And we also saw that the probability distribution function has to be greater than 0 for all I. Now we're going to talk about continuous random variables. So as an example, we might have a probability density function like this. The probability that x, our random variable, lies between two values, so let's just say that's a and b. We don't sum the area of the bars in our histogram-like plot. Instead, it's the area underneath the curve. Area for continuous curves is analogous to summation when we have discrete variables. So if we want to calculate the probability that x lies between a and b, we would just integrate f of x dx between a and b. We also have similar restrictions on the density function. We have that the f of x has to be positive for all x values. The integral over the entire domain has to equal 1. And again, we don't necessarily have to go from negative infinity to infinity. We might be constrained 0 to 1, but regardless, if you integrated from negative infinity to infinity, the integral or the area underneath the curve would be 1. Also, it's really important to note that with continuous probability distributions, that the probability that our random variable identically takes on any value is 0. And that's really confusing to a lot of students who learn probability for the first time. If we're saying that the probability that x, our random variable, takes on the value of 4, that's 0. All right, so it's identically 0. Usually we're interested in what's the probability that our random variable takes on a value between two numbers. And so that's given by the integral up here. Let's take a look at an example. We have a density function here, f of x, and the equation might be given by f of x equals 3 times 8x minus x squared, quantity divided by 256, and our domain is between 0 and 8. We could integrate this and make sure that it's a probability density function. And when you integrate this over the entire domain, 0 to 8, it equals 1. What if we wanted to determine the probability that x lies between 1 and 2? So that yellow shaded region here. We can just integrate our f of x between 1 and 2. And when we do that, we get about an 11.3% chance. So the probability that our random variable will lie between 1 and 2 is going to be about 11%. Similar to cumulative distribution functions with discrete random variables, we can do this for continuous random variables. This is the area under the density function from the left of the range of x up to a given value of x. Capital F of x, the cumulative distribution function, is the probability that our random variable is less than or equal to x. So going way down on the left side, its entire domain on the left side, all the way up to x. So we're just integrating from negative infinity to x. For example, the cumulative distribution function up to x equals 2 would be the probability that x is between 0 and 2. And that's shown by this green region here. We would just integrate from 0 to x. And that would be our cumulative distribution function. And here we would get about 15.6%. If we plotted this, capital F of x, we always start at 0 at the lower end, the left end of our domain x. And as we go to the upper end of our domain, the cumulative distribution function goes to 1. And so each of these points represents the area underneath the curve from 0 up to x. A few slides ago, I showed you how we can determine probabilities based upon integrating our f of x dx. You can also use the cumulative probability function, capital F of x, to determine these probabilities. So earlier we showed that the probability that x is between 1 and 2 is the integral from 1 to 2 of f of x dx. But we can also calculate this as the cumulative up to and including 2 minus the cumulative distribution of 1. And graphically and mathematically, that's exactly the same. And we'll use this quite a bit when we talk about the normal distribution. The mean of a continuous random variable, instead of summing x times f of xi, as we did with discrete random variables, we're just taking the integral of x times f of x dx. For our example, we could do this in Mathematica or something, and we would get the mean is 4. The variance is given by the integral of x minus mu quantity squared times f of x dx. And again, if you have a complicated function, you have to do this numerically, typically. And we get a variance for our example of 3.2. And just keep in mind that sigma is the square root of the variance, and that is known as the standard deviation. One example of a continuous random variable is the uniform distribution. Between a and b, that's our domain, the area underneath this curve has to be 1. So that means the function value has to be 1 divided by b minus a. For any value between a and b, the density function is exactly the same. So it's going to be the same regardless of whether you're down towards a or up towards b. The rand function in Excel, by the way, randomly outputs a number between 0 and 1. Each time it has the same probability. So that is an example of the uniform distribution. The mean of this would be a plus b over 2, and the variance is given by a minus b quantity squared divided by 12. We can also determine the cumulative distribution function by integrating that, and we get x minus a divided by b minus a. I want to just real quick outline a couple of the different types of distributions that we're going to see, continuous distributions. We have the bell curve, also known as the normal distribution. We might have continuous distributions that look like this. So that might be the gamma distribution. You can also have something known as the beta PERT. There's different PERT distributions, but you're constraining the domain to between, for example, 2 and 10. Sometimes people will use a triangular distribution where it's basically these lines here and it's a triangle, and that has a finite domain. And there's lots of other types of continuous distribution functions. So hopefully you learned a little bit more about continuous variables and distributions. Thanks for watching.